A standard web application operates on a highly deterministic request-response cycle. A user clicks a button, the front end sends a request, the API queries the database, and data returns in milliseconds. This standard architecture diagram maps predictable flows, but plugging an autonomous LLM agent directly into this backend API breaks the system. Agents search, loop, and process iteratively. Holding an HTTP connection open while an agent thinks blocks server threats, causing immediate timeouts and cost spikes. Traditional backends are built for speed and absolute predictability. AI agents, by their very nature, are slow, non-deterministic, and highly susceptible to getting stuck in infinite loops. Deploying a reliable AI application requires abandoning the concept of the backend as a simple data delivery pipe. The backend must be reconstructed into a fortified, defensive orchestration layer. This new architecture diagram begins with a user node and an API gateway. For this build, we assume the prerequisite front-end hygiene is already in place. CORS is configured, inputs are sanitized, and basic rate limits are active. Software as a service requires strict multi-tenant data isolation. A basic authentication token confirming a user is logged in does not prevent a flawed database query from returning another customer's data. To solve this, we implement row-level security, or RLS, directly at the database layer. Every single table requires a tenant ID, acting as a physical barrier separating rows of data. If a developer pushes a buggy query, or if an autonomous agent writes a rogue script, the database itself enforces the boundary. One customer's data cannot cross-pollinate with another's. Next, we have to enforce financial constraints. SaaS relies heavily on subscription and usage-based billing models, making compute management a hard requirement. We insert a dedicated middleware block right at the gateway to check a user's subscription status before passing any API call to the system. This block connects to a billing webhook. If a payment fails, that webhook is configured to instantly revoke API access, completely cutting off free usage by resource-heavy agents. Absolute data boundaries and strict financial validation must be guaranteed before a single line of AI logic is allowed to execute. A traditional database query resolves in under 50 milliseconds. An agentic task, like searching the web or processing a large batch of files, can take several minutes. Watch this HTTP request stretch out on the timeline. If you attempt to hold a standard request open for 60 seconds while waiting for an agent to finish its job, the connection snaps. To fix this, we strip out synchronous processing entirely. We route all agent tasks through an asynchronous message broker, utilizing a task queue like Redis or Celery. Instead of waiting for the task to finish, the API immediately fires back a 202 accepted status to the front end, along with a unique job ID. The server thread is instantly freed up, but the front end still needs a mechanism to receive the completed output once the agent actually finishes. Rather than relying on the front end to continuously poll the server, we establish a separate Websocket connection. When the task is done, the queue pushes the result directly to the user. Asynchronous message queues safeguard server threading. They detach the user experience from the inherently slow processing times of LLM chains. When agents are equipped with tools, specifically the ability to write and execute code via a Python interpreter, the security threat profile scales exponentially. We mandate strict tool execution sandboxing. Here, a dedicated agent execution block is surrounded by an isolated Docker environment. You must never allow an agent to run an eval function on your primary server. These execution environments must be completely severed, with zero network access to your internal virtual private cloud. Beyond execution security, hallucinating agent loops introduce a direct financial threat. A single run can call an expensive model 1,000 times in a minute, draining your API credits before you can react. We enforce token governance by attaching hard circuit breakers directly to the agent's internal loop. These breakers monitor the run. If the session exceeds a hard dollar amount, or if it hits a maximum iteration count, the circuit breaker triggers and automatically kills the process. Unlike a standard stateless chatbot, an autonomous agent needs to execute multi-step workflows. It has to remember exactly where it is in a long chain of events. We integrate a persistent thread store, utilizing a state management framework like LangGraph. This allows the agent to continuously write checkpoints of its progress. If the server restarts or a task fails mid-execution, the agent reads the persistent state and resumes precisely from its last checkpoint. It avoids rerunning the entire expensive chain from the beginning. Finally, we must handle prompt injection, where user input attempts to hijack the system instructions to generate malicious scripts or leak personally identifiable information. We place a guardrails layer directly on the exit path of the sandbox. Every final output generated by the agent is sanitized before it ever reaches the front end. The execution layer must be treated as hostile territory. It requires redundant layers of confinement, strict financial caps, and aggressive output sanitization. Standard application logs that record when a user clicked a button or logged in provide zero visibility into why an LLM made a specific decision. To debug non-deterministic behavior, basic logging is replaced by deep observability and tracing frameworks. On the diagram, you can see telemetry lines capturing data from the agent and feeding it into a tracing dashboard. This records the exact chain of thought, the specific tool calls, and the exact prompt inputs the LLM utilized at every single node. When an error occurs in production, you can visually replay the agent's entire decision tree to pinpoint the exact moment the hallucination started. Without deep observability, a non-deterministic system cannot be reliably managed or scaled. Every single error becomes an unsolvable mystery. Notice the sheer volume of infrastructure built purely to contain the agent. We engineered 3 distinct zones: the SaaS API for data isolation and billing, the Async message broker protecting server threads, and the defensive sandbox executing untrusted code. Wrapping a basic API call around a model is simple. Building a production-ready AI backend is an exercise in extreme defensive engineering. Success in the agentic era relies on how strictly you govern resources, isolate execution, and manage persistent state.